Okay, let's take a moment and go through how to do some Lewis structures. The first example we're going to do is phosphorus trichloride. As we look at the guidelines for Lewis structures, step 1 indicates count the total number of valence electrons for all the atoms in the compound. Valence electrons are the electrons that are in the highest principal energy level, which would be the same thing as saying the highest N value would determine the number of valence electrons. If we look at the periodic table, we can readily determine the number of valence electrons. Highest N value essentially restricts us to the electrons, only those that are the S electrons and also the P electrons would be valence electrons. For phosphorus, since we find phosphorus right here on the periodic table, that's going to be 1, 2, 3, 4, 5 valence electrons for phosphorus. Chlorine, being 2 columns further over, has 7 valence electrons are located in a chlorine atom. So in our structure, there's 5 valence electrons for a phosphorus plus 3 times 7, because there's 3 chlorine atoms. For 21 electrons plus 5, it gives us 26 electrons that we would consider valence electrons for this structure. Continuing through the Lewis structure guidelines, we now are at the point where we draw a skeleton structure. Skeleton structure places the central atom, which is typically the first atom in the formula, except when it's hydrogen. Hydrogen cannot be a central atom. In this case, the central atom is going to be phosphorus, and then we draw a line representing a bond to each one of the atoms in the structure. At this point in time, this would be our skeleton structure. We know that we have 26 valence electrons available for our compound. The next step says determine the number of electrons that are still available. Step 3. To determine the number available, we subtract 2 electrons for each line that we drew, and that each line represents a single bond. In this case, there's 3 bonds, so we're going to subtract 6 electrons from our total. At this point, we now have 20 electrons remaining to still do some bonding or be part of the structure. And that 6 electrons are already taken up by 2 electrons in each individual bond that's connecting chlorine to a phosphorus. We now need to determine how many electrons are needed to complete the structure. To follow the octet rule, each atom needs to get 8 electrons surrounding it. By getting 8 electrons, an atom gains an electron configuration, isoelectronic with a noble gas, which is a very stable arrangement, and that's what all atoms desire, and that's why they're going through the process of making a compound. Each bond counts as 2 electrons, so we can see chlorine needs 2, 4, 6 more electrons. Phosphorus, because it has 3 bonds around it, already has 6, so phosphorus needs 2 more, and this chlorine needs 6, this chlorine needs 6. Adding this all together, we end up with, we have 6 times 3 plus 2, so we have 20 electrons that are needed to complete this structure. When we check the guidelines, it indicates that if the number of electrons available is equal to the number of electrons needed, the next step is to distribute the available electrons around the structure to complete the octet for each atom. By distributing the electrons, we complete the octet for the chlorine atom over here. We complete the octet for phosphorus. We complete the octet for this chlorine. And so far we've used 2, 4, 6, 8, 10, 12, 14 of our electrons. There's 16, 18. We've used up 20 electrons. That completes our structure. And this would be the Lewis structure for PCl3. Here we'd have the finished structure for our molecule PCl3. Let's go to our next molecule, NO3 1-. Step 1, determine the number of valence electrons. We can find nitrogen and oxygen in the second period on the periodic table. And once again, counting valence electrons is essentially counting over to all the s and p electrons that are in the valence shell. Valence electrons, once again, are electrons of highest n value, or the highest principal energy level only. So we have 1, 2, 3, 4, 5 valence electrons for nitrogen and 6 for an oxygen. So in determining our valence electrons, there's 5 for the nitrogen, and we have 3 times 6 for the oxygen, plus 1 additional electron because of the -1 charge on our compound. That means we've added in an additional electron to the structure to give it that -1 charge. When we add together all of the valence electrons, we find that for this structure we have 24 valence electrons. The next step is now to draw our skeleton structure. Once again, the central atom is the first atom in the structure, so we have a nitrogen, an oxygen, an oxygen, and an oxygen to give us our skeleton structure. We've determined for this structure that there's 24 valence electrons. We now subtract from that the number of electrons that are in bonds, where each bond represents 2 electrons. Since our skeleton structure has 3 single bonds, we're going to subtract 6 electrons. This leaves us with a total of 18 electrons that we would say are available to continue to do work or contribute to the structure. Our next step is to determine how many electrons do we need to fill the octet surrounding each atom in the structure. Each bond counts as 2 electrons. So here we have our oxygen. This oxygen requires 6 more electrons to complete its octet because the bond that it has counts as 2 electrons. Our nitrogen in the center has 3 bonds around it, each one counting for 2 electrons, so the nitrogen needs 2 electrons. This oxygen also needs 6 electrons, and the oxygen over here needs 6 electrons. So we have 6 plus 6 plus 6, 18 plus 2, so we have 20 electrons that are needed to complete this structure. The guidelines indicate when the number of electrons needed is greater than the number of electrons available, then we have to add extra bonds to the structure. This is when compounds develop double and triple bonds. For every pair of electrons that were off between needed and available, we add 1 additional bond to our skeleton structure. So we'll toss in an extra bond between the oxygen and the nitrogen. We now have to recalculate how many electrons we have available and how many are needed to complete our structure. In this structure with the extra bond, there's now 4 bonds in the structure. Each one's 2 electrons. We subtract 8 from our 24 valence electrons we have, leaving us with 16 electrons available to continue to work on the structure. We recalculate how many electrons are needed to complete the octet for each atom. Our oxygen on the end here, because it has 2 bonds on it now, only needs 4 more electrons to fill its octet. The nitrogen needs 0 electrons because each bond counts as 2. It has 4 bonds around it. This oxygen requires 6, and this oxygen needs 6 electrons to complete the octet. 6 plus 6 plus 4 gives us 16 electrons that are needed. And when the number needed and available become equal to each other, that indicates that we now distribute electrons to complete the octet in our structure. Fill in the electrons on each atom. 1, 2, 3, 4. The nitrogen needs 0. Here we have 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We've completed the octet for each atom. We've used up our 16 electrons we have available, and this would be our Lewis structure. Whoops. Let's back up. Since this is a negatively charged ion, there's a second part here. Ions get bracketed in, and then outside the brackets of the ion, we write the charge. That indicates that this particular structure has a charge on it versus being a neutral compound. This would now be the proper notation for our NO3 Lewis structure. Let's move on to another structure. We have astatine trifluoride. Step 1, determine number of valence electrons. Both astatine and fluoride are in the halogen column on the periodic table. All halogens have 1, 2, 3, 4, 5, 6, and a seventh column. They all have 7 valence electrons. If we combine these together, astatine has 7 valence electrons. Each fluorine has 7. And there's 3 of them. That gives us a total of 28 valence electrons in this compound. Our next step is to draw our skeleton structure. We put astatine at the center, and we draw a single line to each one of the atoms in the structure. So at this point, this would be our skeleton structure. The next step, looking at the guidelines, is we have to determine the number of electrons still available. We have 6 electrons used up in bonds, and that each single bond utilizes 2 electrons. So we have to subtract 6 electrons from our total, which leaves us with 22 electrons that are still available to contribute to our structure. Next thing in our strategy is determine how many electrons are needed to complete the octet for each one of the atoms in the structure. Our fluorine here needs 6 electrons. The astatine needs 2. This fluorine needs 6. The fluorine on the bottom also needs 6. That gives us a total of 20 electrons that are needed to complete this structure. In this structure, the number of electrons available is greater than the number needed. In that circumstance, the guidelines indicate we're going to have a structure that violates the octet. In that, when we have more electrons available than are needed to complete the octet for each atom, any excess pairs of electrons are placed on the central atom in the structure. We place the electrons around the structure. We fill in 6 on one fluorine, another 6 on another fluorine, 6 more on a third fluorine, and we put a pair on the astatine. That takes care of our 20 electrons that are needed to fill the octet, but it leaves us with 2 extra pairs of electrons. Because we have 22 electrons available, the 2 extra electrons are placed on the central atom, and the central atom violates the octet rule in this circumstance by having 10 electrons around it, which is possible for some structures. So our final version of the structure, once we've placed all electrons, valence electrons on the structure, distributed the extras by putting them onto the central atom, this would be our structure that we have for astatine trifluoride.